Hello everyone, this is section 15.2 part 3. Last time we saw this example where we looked at integrating, finding the value using both a region 1 and region 2 method. And so we went through both situations and we saw that we get the same result, of course. So a little bit of tedious algebra, but nothing really complicated. And so now we'll look at some more examples. And the next example, remember we always have to sketch the region. And so this one is integral of x minus 1 over the region in quadrant 1 bounded by these two graphs. So the first thing is to make the sketch. So off to the side. Okay, we should know what the graphs of these two functions look like. I mean, obviously, y equaling x is just a straight line in the first quadrants. We could actually find the points of intersection if you wanted to, but you could do this pretty much by inspection, because you know that when x is 1, they're going to be the same value. And you know what the graph of y equaling x cubed looks like. That's just a function that basically x cubed looks like this, right? So we should know about that. So we can get this one pretty easily without having to go through formally finding the points of intersection. When x is 1, y is 1, and that's going to be the straight line, y equaling x, and then the cube root of x, okay, that comes in from below, crosses the origin, dips up here, because like if x is 1/2, for example, 1/2 cubed is 1/8, so it's really down here. Okay, so that's pretty much what the graph of y equaling x cubed is going to look like. And then we'll decide what type of region we want to choose to use. And because everything's given in terms of x, if you don't have to split the integral up, if you don't have to change functions, then it's probably going to be wise to fix x, and that would mean we'll use vertical strips. So let's draw a representative vertical strip, and it looks like that's going to work out nicely. So we'll use a type 1 region where x is fixed. And so we'll have the double integral over the region of the function x minus 1 with respect to the region 0 is the double integral of x minus 1. Since we decided to fix x is the outer, so dy dx. And then we can fill in the limits of integration for x. That's just going to be 0 to 1, so as x ranges from 0 to 1, all of these little vertical strips gives you everything you're looking for. And then lower function looks like it's x cubed, and the upper function is x. Okay, so that's the appropriate setup. And now just do the calculus. This one's not too tedious. Go 0 to 1. Integrating x minus 1 with respect to y. Both are constants, so we get xy minus 1y, or xy minus y. And now that's as y ranges from x cubed to x. And then all of that with respect to x. Fundamental theorem of calculus, 0 to 1. Upper limit goes in, so an x goes in for y. we get x times x, and then minus x, minus lower limits x cubed going in for y, so x times x cubed, minus x cubed, and then all of that will be with respect to x. So let's see, that gives us the integral from 0 to 1 of, keep the brackets for now, and the parentheses, x squared minus x, minus, then we have x to the 4th, minus x cubed. Okay, not much we could do there. We'll just have to grind through this, and we get close my parenthesis there. Okay, so take the integral from 0 to 1 of, then we'll just have x squared minus x to the 4th minus x cubed, nothing to combine. That's all with respect to x, equal to, let me get this portion of the graph out of the way. Didn't really give myself enough room, but we're good. Now integrating, and so that's going to be 1/3 x cubed minus 1/2 x squared minus 1/5 x to the 5th, and then minus 1/4 x to the 4th, all evaluated from 0 to 1. And just in case you can't see that clearly, that's a cube. Okay, and now fundamental theorem on that. Plug in the 1. I'm not going to show it explicitly. We get 1/3 minus 1/2 minus 1/5 minus 1/4, and then all minus, if we're putting a 0 in for x, everything there goes to 0. So just call it a big 0. And then if you take the 1/3 minus 1/2 minus 1/5, oh, I'm sorry, that would have been a plus 1/4. So make this correction. At this stage, I neglected to distribute the negative here. So that would have been a plus. This would have been a plus. And that would have been a plus. Okay, and then use a fraction calculator or grind it out. Get minus 7/16. Okay, so occasionally here it's convenient to reverse the order of integration. And so if you have to, definitely make a sketch. Okay, so sketches are crucial in this section. This one's really easy because look at the region is rectangular. So if you draw the rectangular region, it's from 0 to 3 in the y. Okay, so the inner is the y based on the, so 0 to 3 in the y, and 0 to 2 in the outer, that's the x. So that's just a rectangular region. And so if we want to switch the limits of integration, it'll be the double integral. I didn't even put a function in there, just call it in general some function of x and y. Okay, so now instead of dy dx, we want dx dy. And, excuse me, we can just simply think it goes from 0 to 2 in the x. Those are now the inner, and 0 to 3 in the y. So those are the outer. Okay, for the next one, make the graph. And let's see what we're dealing with here. So we're going from x, so that's y equaling x. So the lower limit is y equaling x. So that's just going to be, and then we're going to 2. So y is 2, high point. x is going from 0 to 2, so let's just scale that off. Alright, and then let's draw the line y equaling x. So when x is 1, that's not a 0. When x is 1, y is 1. Yeah, when x is 2, y is 2. So there's y equaling x. And so we're going from x to 2 is the y. So that means from the function up to 2, so we'll have to draw a horizontal line at 2 here. That's y equaling 2. So y equaling x and y equaling 2, or that's the lower limit and the upper limit of the that are functions of the limits of integration for y. Just cheating a little bit here with regards to where the point was. Let me move the 2 over. No big deal, it's just a sketch. But to know what region we're looking for, that's going to be from this, because it's x is the outer limits of integration. We're going from 0 to 2, and then the function x to 2, so that's going to be this triangular region here. Now, these limits are set up to be with regards to horizontal strips. Or I'm sorry, they're set up to be with regards to vertical strips. So something like this. That's how the given is, from x, lower limit, to 2, upper limit in terms of y, and then x ranges, because it's the outer, from 0 to 2. We want to change to vertical strips. Okay, so now the double integral of whatever that function is, if we do x first and then y, now we have that x is ranging from x equaling 0. Okay, if you want to do y's first, let's do the y's first. So y goes from 1 to 2, 0 to 2, no doubt about that, right? Because to get from here to here, cover all that, 0 to 2. Okay, so that's for sure. But now x. Okay, so x is starting over here. That's where x is 0, the vertical line. So we're starting at 0, and we're going to the line. And the line is y equaling x. But y equaling x is the same as x equaling y. So therefore, because we need this x in terms of y, the upper limit is going to be y. Alright, so those two are argued rather simply. And now this one a little bit more interesting. I'm going to draw the graph directly below. Okay, and we basically have x squared over 2, which is a parabola, and a straight line, 2x. X is going to range from 0 to 4. So, obviously the y-axis is 0. Let me call this 4. In terms of the parabola, y equals, okay, so we're dealing with y equals x squared over 2, and we're dealing with y equals 2x. So, if y is x squared over 2, put in a 4, we get 16 over 2, or 8. So let me call this 8. That's going to be a point on the parabola. And then, if you look at the point on the line, if x is 4, 2x is 8, that's the same point. We know the line passes through the origin, because there's no y-intercept. So let's draw that. Okay, so that's our line, y equaling 2x. And then the parabola. So we already said about the 4. Let me see, what if I'm at 2? If I'm at 2, the line is at 4. Where's the parabola? 2 squared is 4 over 2 is 2. So I'm down here. Then it goes through the origin, and then symmetry. So let's just draw it. And there's the graph of our parabola. Y is x squared over 2. Okay, now we need to change the limits of integration. But note that to change the limits of integration, we need x as a function of y. For both situations, the line and the parabola. And so let's say for the parabola, I'll label it as 1. Y is x squared over 2. Solve this for x. We get 2y is x squared. So then x is plus or minus the square root of 2y. Excuse me. But what we're dealing with is the positive version. So that parabola, in terms of that half, is x equals positive square root of 2y. And this half is the x equal negative square root of 2y. So we're going to use, obviously, the positive version. For the line, y equals 2 over 2x, there's no problem at all. Just solve for x, you get y over 2. Okay, so now the double integral. So the double integral of the function f of x, y. Okay, we're switching them, x first, y second now. And so, okay, you want to get rid of the y's first. That's going to be the constants. Y ranges, because now we're taking horizontal strips rather than vertical strips. Okay, so y ranges from 0 to 8. So covering the whole y region with those horizontal strips. And let's see, left-hand end points the line, but the line is now, in terms of x, it's y over 2, as we had solved for over here. So y over 2 is the lower limit. And then the upper limit's the parabola, but the positive part of it, so the square root of 2y. Okay, let's get started on the next problem. And the next problem is, I just called these more examples. So I think we're going to need one more part, but let's get started to this lesson. But getting started on this, what we want to do is we want to identify the regions of integration, set up the integrals, and I'm just going to draw a circle here. So the figure that we're going to work off of is just going to be a circle centered at the origin with a radius of 4, or excuse me, of 2. So I'm just going to draw a circle centered at the origin, and I'm going to say my radius is equal to 2, so that the top half is going to have the equation y equaling the square root of 4 minus x squared. So that's the top half. And the bottom half is going to be minus the square root of 4 minus x squared. So that came, of course, from just taking x squared plus y squared equaling 4 and solving for y in terms of x. So y would be plus or minus square root of 4 minus x squared. Okay, so that is our sketch, and that you can consider to be a given. And I'm going to label the regions as follows. In the first quadrant, I'll label it Roman numeral 1. Second quadrant, Roman numeral 2. But then I want to consider this to be Roman numeral 3. Okay, both pieces here. Okay, so Roman numeral 3 is going to represent quadrants 3 and 4. Okay, and the first part of the question, we want to set this integral up with respect to type 1 integrals. So if we're doing type 1, then we know that x is fixed. Alright, so the first situation would be for, let's say, for the region that we're in the circle that we're labeling as Roman numeral 1, not to be confused with the type 1. So that would be the integral. Okay, if x is fixed, remember that means that x is going to be the outer. So we're taking the double integral. The function, we're working with the top half. Well, I mean, that's going to be involved in the limits of integration. We're just going to say that we're going to integrate this over 1. So if we're not going to have a function that we're integrating z. Let's say if you wanted to take z equaling f of xy to be equal to 1. So that if it's a type 1 where x is fixed, it's going to be of the form dy dx. And if x is fixed, and we're working on this region here, then we want vertical strips. So let's consider vertical strips in this region. Now remember, this is where x is 2 at this point, because the radius is 2. Okay, so this is going to be 2, this is going to be positive 2, this will be a negative 2 over here, and this will be a negative 2. Okay, and we're taking vertical strips in that region. So we're going from, if you want to take care of the x's first, we're going from 0 to 2, because that's only this little Roman numeral 1 region. So the outer limits are definitely going to be 0 to 2. And then the inner limits are going to be whatever this vertical strip gives us. And we're going from y is 0 now, so that's at the x-axis, to the function. And the function in terms of x is the positive square root of 4 minus x squared. Okay, so I think I'll stop right there, and we'll come back and obviously finish this up, and then hopefully get through the rest of this unit in the rest of this section in one more part to the video. So we'll see you when you're ready.